validation. So this is the outline of the presentation. I will describe to you the extrusion blow molding part, the motivation of the work, the simulation tools we use. In this case, we'll be validating the clamping and inflation, show you what we have done in terms of experimental validation and some conclusions and plans for future work. First of all, for those of you who are not familiarized with extrusion blow molding is not the technique used to manufacture these bottles, but okay, somewhere close. We start with a tubular profile, as illustrated here. There is a number of molds that close, fix that tubular profile, then it's cutted, and there is an insert that blows the material and it conforms to the mold. So there are a number of phases, the process, the extrusion, the clamping, the inflation, and then the cooling and the trim. This technique is widely used in industry, but there are just a few codes available to deal with that. And the main limitation of those codes is that they are not allowed to model all the phases. And if you think about optimization, we need to model all the phases and connect them somehow. Regarding the available softwares, as far as I know, these are the two that can be used for the extrusion blow molding is BSIM, that models just the clamping and inflation, and Polyflow that molds the clamping and inflation. It also molds extrusion, allows to model extrusion, but the phases are not connected. So we cannot think about optimization, and these are our future plans. So that was the main motivation to start working on the extrusion blow molding simulator, the code I will present to you. I will not cover this in detail in this presentation, but to show you that we are just also working on the extrusion phase, when we are the part of the process where the tubular profile is produced, and to do it, we are using OpenFOAM and using an approach similar to VOF, and in this case using differential viscoelastic models. Where we have the governing equations are the mass conservation, the momentum balance, and the constitutive equation, as you heard before, for the couple solver. And in this case, since we are modeling a two-phase flow, there is a phase transport equation. And one relevant detail of extrusion blow molding is that during that production of the tubular profile, the inner mandrel that moves in order to allow us to control the thickness along the profile. And this is what you get if we, in VOF, if we isolate just the polymer part in terms of simulation. And in order to model to mimic the moving mandrel, we used the dynamic meshes from OpenFOAM. And you see here a typical production of the tube with the moving mandrel. Okay. The mandrel moves. It affects the thickness of the tube, of the extruded tube, and this is a 3D or axisymmetric, depending on the kind of geometry we have. But in general, we need to do it in 3D, and then we use utilities that are available already in OpenFOAM in order to map the surfaces in order to get the outer surface of this tubular profile that we call parison. And since we got the outer surface, it allows us to progress to the second phase, that is the mold clamping and inflation. The part where the mold closes and then the tube is inflated. And for that, what we do is we use a membrane formulation, and we took advantage of the finite area approach that is available in OpenFOAM. And to give you a clue, as I mentioned, these codes have been presented before. We even illustrated last year or discussed last year the different approaches for the process. I will mention them here again, but not in detail. But typically what we do, we have the membrane surface, we discretize, we trilliarize the membrane surface, and in order to map the deformation in 2 consecutive instants of time, we map that transformation using a linear, a least squares approach, and that allows us to compute the deformation gradient. And this deformation gradient is used together with a number of models. We have tested a number of models for those cases, basic linear elastic, just to start, hyperelastic models. In this, the one we have used in the results I will show you was the Manu-Rivling, and we have used the total Lagrangian approach. We also tested the viscoelastic ABKZ model, since we're dealing with a Lagrangian approach, makes quite easier to use the Lagrangian, integral viscoelastic models, but due to the time required for the calculation, we didn't progress in that part. Regarding the time evolution, what we do is we use a quasi-static approach, which means that we increase pressure, obtain a stabilized distribution, and go on increasing pressure. This is an approach that is often used in these kind of codes. Give an idea of what you can calculate. Consider we have this container for simulation. What we need the molds, we need the Parison geometry in this case, and we have here is this, what we have illustrated here is the setup for the calculation, and this is the initial mandrel, then the mold. Right now the mold is closing, and then it starts the blowing part that inflates the material. And this is what we can get. Obviously, what's important in terms of one of the important details in terms of calculation is the thickness distribution we obtain for the final container. That we can measure, control, and then adjust, for instance, the thickness of the Parison along its length in production. Okay? Give an idea of what we have done in terms of experimental validation. This is the container we tested, and in order to produce it, okay, the tools were prepared. We used a standard mold in order to produce the final container, but we also created a conceptual mold in order to be able to visualize at least the initial parts of the process to help us figure out which were the possibilities, what was happening. And also we have used the X-ray microtomography to get the outer geometry of the part and the thickness distribution. It's quite convenient to use because it allows us to get a map of the thickness distribution in the container, which was very useful, as I'll show you afterwards, to allow us validating the code. And these are the latest results we obtained in terms of comparison of the thickness distribution of the container with the actual models we use. And you can see we measured the thickness everywhere. We have all the map, experimental map, but we selected a few lines just to illustrate the quality of the results. And you can see from these results that the approach we are using gives us quite close results to the ones are obtained experimentally, which, as I referred before, is an important data for our partners, in this case Logoplast, since they are interested on using intensively these computational tools before progressing to the actual production. So this takes me to the final conclusions of this presentation. Okay, I showed you the codes that are able to model all the process. We have already the link between the different phases, and we validated the mold clamping and inflating phase that allows us to show us that the solvers we have give, at least for this case, obviously quite accurate results. What we need to do, obviously, is to go on validating with other tools and work on optimization approaches, taking advantage of the ability to model all the process. So, acknowledgements also regarding this work, the projects that funded and PhD. It's the work. The numerical part of the work is being done mainly by Wagner Galupo, the first author of this presentation. And thank you. And I'm available to answer your questions, obviously.
Any questions for Professor Dobrik? Is this part of the Excel form?
No.
No. So whether the especially handling free surface, whether the code is also open source?
The codes are mainly there are solvers in foam extent to do it. We didn't, in this case, we didn't perform any significant modifications.
Extrusion molding has been around for a long time, I do imagine. So what do you hope to gain additionally by doing these simulations? Where do you think that you could further optimize?
This project, as I mentioned in the beginning, has been motivated by a company. It's Logoplast is a big company working in this area. They started in Portugal, but now they are in quite different countries. They have at least Brazil, UK, US. They have factories in several places. They face big issues when designing new containers, and they are pushed to design new containers. The process demands a lot of trial and errors, and usually they hardly reach their target in terms of mass for the containers. So, in order to respect the specifications, usually they need to have larger masses than they would like. So they're spending more material, and we're not talking about 1 gram here is a huge amount of money. There are millions of those. What they target is to improve their design approach, and what we also target is the same, obviously, to help them to design better, faster, and reach the specifications of assure that there is a minimum thickness all over the container, but minimizing the amount of material we have. I do remember regarding your question, when one of the persons that went to the company, Logoplast, he redesigned one of the 5-liter water bottles, and he saved, I believe, 1 gram, and it was a revolution in the just for that. For each 1 container, he removed 1 gram for the container, and it was a big revolution at the company. He has been working there for many years, and he obviously knows what are the potential of saving money just by a small difference in terms of the amount of material you spend in each container.
What is it that would be optimized? Is it the shape of the mold, or?
There are. Okay, sorry, I didn't have the time, and I had to skip in many cases. But during extrusion, the mandrel moves, so you are able to control the thickness of the parison along production, and that's one of the biggest problems to solve, because you don't know experimentally where the material that is in a certain position, where it goes in the mold. Numerically, you can. So you are tracking the different portions of material. So one of the issues or the details to optimize is the thickness distribution along the parison, and for instance, the amount of material you have in the container as well. Try to minimize to assure that, because in many cases you want to assure permeability. So there is a minimum thickness you need to assure in all package. So, and this point where it came from, it's not easily identified experimentally. So that's what numerical simulation helps. But mainly the optimization, and we have presented some optimization without the full system, just for the inflation and mold clamping and inflating parts. It's the thickness along the parison. That's the major variable to optimize.
Any more questions? If not, let's thank Professor Lobrick again for
Thank you.